Are we there? Hello. Yeah. So it's been a while, and of course, Microsoft has updated its software and changed the interface of PowerPoint again. And so I have to get used to it. We're doing that. And previously, we talked about all these igneous and metamorphic rocks, those that were involving fire and melting and all that kind of stuff. And now we're going to talk about sedimentology, about sedimentary rocks, which are rocks that typically are formed in rivers, lakes, lagoons, and so on. And this is a very important topic for petroleum geologists, because all those reservoirs that we're producing oil and gas from are formed 99% in sedimentary rocks. So let's go to the next. Oh, I have to take my glasses off, and I have trouble reading the bloody screen. Did you see my Harry Potter new thingies on my head? Oh, okay. Sedimentary rocks. What the hell are that? They are rocks that are formed at the Earth's surface, on the surface of the Earth, in the bottom of the seas, the bottom of rivers, at lakes, in lagoons, that kind of stuff. So it involves deposition of transported minerals, of mineral particles that have been dropped out of water or air. And when we talk about dropping out of air, we talk about aeolian sediments or deposits. And when they drop out of water, we call them aqueous sediments or deposits. And of course, we can have chemical solutions that are high in dissolved salts, right? And then there's often in warm climates where you have a lot of evaporation, then we exceed the solution product, right? The maximum amount of salt that can be dissolved in water of a certain type. And then we can drop off things like salt, NaCl, rock salt. Or we can create potash. Okay, and then the third way of forming deposits is through biological activity. Animals that grow together and form, say, a colony, like reefs. Okay, so let's have a closer look at that. And I'm gonna activate my pointer. So we have several types of sediments or deposits, right? We have clastic sediments, biogenic, and chemical deposits. You notice that I intermix the word sediment with deposit, right? It's the same thing. So clastics are rocks that have been reworked, pre-existing rocks that have been reworked and weathered. And then the erosional products, the boulders and the cobbles and the pebbles and the sand grains and then the very fine-grained clays have been transported, typically by water, right, by a river or by waves in the sea, to a location of deposition where they dropped out and formed a clastic deposit. Now you can have also, especially in warmer climates, you can have creatures, animals, right, that create a framework of materials, often limestones or dolomites. And the dolomite is typically the altered or diagenetic product of limestone. We'll talk about that later. Right? And those sediments we call biogenic. And then, of course, you can have an area with water that is highly concentrated in salts, right? Like due to evaporation, a lot of water is evaporated and the salts remain in place, still in solution, and then the salinity of the water body goes up. Seawater is pretty saline, but if you can go on line like here on this lake, right, and then a lot of evaporation can also increase the salinity of the solution, the water in the lake, and then it precipitates, it crystallizes out and creates a chemical or evaporite deposit, precipitation from solution. Oh! So we have clastics, carbonates, which are often related to biogenic processes, and evaporites, the precipitates. Clastics are often materials or deposits formed from reworked pre-existing rocks. These rocks have been eroded away and weathered and broken down into particles and transported and abraded and made smaller and smaller, and then they reach a point, a locus of deposition, where they fall out of the fluid or the air that transported them to this place, and then they form sandstones or shales, and those happen to be formed often on sandy beaches, on shorelines, but also in rivers and at the bottom of lakes. These are called the clastics, and typically they're sandstones or shales. And really the difference between the sandstone and shale is typically the grain size. If you're below, say, 5 or 10 microns, then we call the rock typically a shale, and it is very rich in clay minerals. Sandstones, well, can be subdivided into siltstones and sandstones, and again, that is a difference in grain size. The boundary between sandstones and siltstones lies typically between at 60 microns, or 62 microns to be precise. That's the Wentworth scale, and we will talk about that later. So carbonates are limestones, and if they get diagenetically altered at temperatures below 200 degrees, so it's diagenetically altered, not by melting or partial melting, right? It is just chemically altered. Often one of the calcium ions in the limestone, which is calcite typically, right, is being replaced by magnesium, and it changes the crystallinity of the rock, and therefore the volume and the porosity. Okay, that is also a diagenetic process, right? And so limestones get altered and changed at temperatures below 200 degrees Celsius into dolomites. Smearmittel, yeah? Lubricant. Okay, then also we have evaporites. So we have hypersaline waters, often in lagoons and things like that. And then the salts dissolved in the water are so highly concentrated so that they exceed the solubility product, the solubility of the water, and then it starts dropping out, crystallizing, precipitating from the water. And typically you get things like NaCl, right? Potassium or sodium chloride, which forms rock salt. Or you can have sulfates like gypsum and anhydrite. The difference between gypsum and anhydrite is that the gypsum holds water in its crystal structure, while the anhydrite, the water has been removed. And it's the same stuff, but without water in it. We call it anhydrite. And then you can get potassium chloride. And very famous for that are the potash deposits in Saskatchewan, right, over the border. And you can even find potash there at the surface along ponds that are all coated with white stuff. And then the white stuff is the potash. Okay, next step, carbonates. Carbonates are typically limestones and dolomites, with some clays, shales interbedded, right? And there's a mixture of lime and shale, and we call that marl, right? Those carbonates are typically formed by biological activities. And the most famous example is something built up by animals. It's biogenic, and they are known as reefs. Yeah. You can also get algae building up thinly laminated limestones, and we call them algal mats. Then you can have fairly high concentrated calcite solutions, often still normal marine, and then the calcite precipitates out in concentric circles around a little core grain, a center of precipitation, and that grain can be a little quartz grain, or it can be a fragment of a skeletal part of an animal, or a part of a broken shell, that kind of stuff, right? And ooids are typically deposited on shoals or beaches where the water has a relatively high energy level, and that is helping when it precipitates the calcite to form those oolitic concentric circles. Okay, and then you can have, of course, pre-existing limestones that were broken down and weathered and broken and transported, skeletal material, pre-existing ooidal sandstones, etc. And these particles, transported typically by water, are then forming a form of a clastic deposit, but because they predominantly comprising calcite and dolomite particles, we still consider them limestones, reworked limestones and dolomites. And then the dolomite is basically a diagenetic product where the calcite, which is Ca2CO3, right, where the calcite ion, one of the two, is replaced by magnesium. Diagenetic altered dolomites. Okay, I'm going to take a break. So we're back. And we're going to throw some more terminology at you. Lubrication. And we have to talk about diagenesis and lithification. Diagenesis is a sum of physical, inorganic, chemical, or biochemical changes in a sedimentary deposit after its initial accumulation, and is excluding metamorphosis, right? Remember, metamorphosis is at temperatures above 200 degrees and below 200 degrees, those chemical processes and biochemical changes, etc., that is called diagenesis. And then we have another term that geologists often use, and that is lithification. Okay, when a rock is glued or cemented together into a solid entity instead of loose particles, then we call that lithification, changing loose particles into a rock. Okay. Now, okay, I removed myself from the picture because this is a fairly complex picture. Although we call this the simplified Dunham classification, which was created in 1962 by a geologist from Royal Dutch Shell. And Shell has made a lot of contributions to the science of geology, despite being a commercial oil company. And you'll find that coming through over and over again. Okay, but here we have the simplified Dunham classification, and there are two parts. This is the Dunham classification that is for limestones with particle size typically less than 2 millimeters. And then you have here an augmented classification. Oh, where's my pointer? Here is an augmented classification where the particles involved, the grains involved, are typically greater than 2 millimeters. At least 10% of the grains is over 2 millimeters. Okay, let's first start here at the simplified one. And we have original components not bound together, right, just dropped out of the water during deposition. And then we can have portions of the rock types that contain mud, lime mud, so like a clay, but now completely calcite or dolomite, but the particles are less than 2 millimeters. In fact, they're less than 10 microns typically. And then you have rocks that have no or very little mud, i.e. particles that are 10 to 5 microns in size. Right? And if the rocks completely are made out of mud, that fine-grained material, and with less than 10% grains in them, then typically it looks like a mudstone. It's massively white, very fine-grained stuff. It's a mudstone. If you get particles floating in it, but it is less than 10% of the rock, then we call it a wacky stone. If you get more than 10% grains, then the rock starts to form a skeleton of particles, a framework of particles with spaces in between. And those spaces can be still filled in by mud. And then we call it a wacky stone. And if there's less than 10% mud in the rock and the pore spaces in between the particles are staying open, then we call it grainstone. And also we have rock that has been bound together by biological activities, like for example algal mats that create laminated rocks or reefal materials, right? And we call that a bound stone. Now, if you have coarser than 2 millimeter particles typically, then we subdivide the rock into allochthonous and autochthonous rocks. Allochthonous means that the material that comprises the rock has been typically carried in to the area of deposition from outside that area. Right? That's why it's called allochthonous. It's not from here. It's not locally derived. And autochthonous is locally derived materials. Yeah? And often they are bound by biogenic processes, the autochthonous ones. While this is more like a clastic rock, where stuff has been dumped loose together, right? And if we have, just like in the original Dunham classifications, if we have particles greater than 2 millimeters in size, then we call it a float stone. It's kind of a wacky stone, right? Because you have more than 10% grains here. It's not all lime mud. And here the ground mass can be coarser than the 5 to 10 microns, as you see in lime mud. It could be coarser, but still a lot finer than 2 millimeter type of carbonates that have been trapped, limestones that have been trapped and form the ground mass here of the rock. If you have more, typically more than 10% grains, then the larger particles are going to form a framework, and then the ground mass is finer material, less than 2 millimeters, and often mud, and in that case we call it a rudstone. That is the allochthonous floatstone and rudstone. Now we're going to look at limestone particles and things that have been bound together by biological activity. And you can start out with seagrass or something like that, something dendritic with often a carbonate and limestone skeleton. And then the water washes in fines that have been baffled in between those organisms. And I call that a bafflestone. If it is more laminated, and it is things like algae that bound together the organisms, or they encrusted the particles, right? And then in between we get a ground mass being trapped again, then we talk about a bindstone. And if it is a series of animals that build a framework, right, such as a reef, then we call it a framestone. Wow. And so now we're going to go a little bit more complex. And I really don't understand. So now we're going to make it a little bit more complex. Not really that much more. But in A, we have the simplified Dunham classification, and then there is a field also for the bound stone that we talked about. And the problem is that you see here, depositional texture is recognizable. Well, why wouldn't it be any longer recognizable? Well, that is when it is exposed to recrystallization. So that is during deposition or after deposition, kind of like diagenetically, the rock gets recrystallized. And then you cannot recognize the original texture so well. Right? Here's my point. So this is textural, but it starts to get recrystallized, but the textures are still recognizable. So we're sticking with the original Dunham classification, right? And once it is no longer recognizable, once the texture, the recrystallization has taken over so much that you can't recognize the components that help us identify it according to Dunham, then it is a recrystallized carbonate or a crystalline carbonate, either limestone or dolomite, right? This stuff here is when it has not been recrystallized, and then we have the allochthonous limestone with the simplified Dunham. And then if the particles get greater than 2 millimeters, we start using the terms floatstone and rudstone. And then we leave out the bindstone a little bit, focusing on the autochthonous limestones, where the original components are basically are locally derived. And then you have framestones, bindstone, and bafflestone. So it's a little bit more complex than before. And by now, if you stand in the field, you'll have a hard time to recognize what you're actually looking at. Sorry. Anyway, we're going to stop here.